Hello?
Hello.
What's up, that guy? Oh, you need that? Back there on the shelf, see those boxes of broken calculators? Okay, see where the rulers are? Keep walking. Get all the way back there. Okay, now look to your left. There it is, right there. Ah, no, too far. Yes, right in there. Okay, good. All right, so we're finishing 1.5. And for all those YouTube viewers, how do you guys think about my new coffee mug? Yes, this is my new coffee mug. Epic. Anyway, all right, so fine. Limit of this one right here, as it goes to infinity. Now, let's take a look. So, you guys have to think about this conceptually. Because if you try to just think about it numerically, infinity is not a number. So you have to think of it conceptually, right? So every time we're doing this, especially taking the limit as it's going to something. Now, so I'm going to start this off with an idea. I like telling stories instead. So stories usually help explain what we're talking about. So let's say, it's Friday's birthday. Okay? It's Friday's birthday. And Friday's mom brought in cupcakes for everyone. Okay? But she didn't know how many people are in here. So, and Friday forgot to tell her. So, we start off with 20. So there's 20 cupcakes. Actually, desktop tool. Ah, crap. What the deuce? Did I? Dang it, though. I lost the whole thing. All right, hold on. Let me pause this. All right, so, yeah. Okay, so now, story goes, so now there is 20 cupcakes, and we have 20 people in class. So we got lucky, right? So each person now gets one cupcake, right? Yeah. Okay, but now, instead, so accidentally your mom, Friday's mom, drops it off later in the day. Later in the day, he has to go in his history class or some other, liberal class, which is, Anyway, so still got 20 cupcakes, right? But in a different class, there is 40 kids. So now, in that class, oh crap, hold on. You know what? 1. Okay, so then it was 20 over 40, that is 1/2, right? All right. That kind of sucks, right? Half a cupcake for each person. Okay. But, it's still not bad. But now, we still got those 20 cupcakes. But now, instead, Friday's mom brought it on a day that we actually had an assembly. And she delivered it during an assembly time for some reason. I don't know. He forgot to tell her what time class was. And so we're in an assembly, and in that assembly, she just walks up in there with cupcakes and say, hey, and expects everyone to start singing happy birthday to Friday, right? And so not realizing that there's 2,000 students in there. But she still only brought 20 cupcakes. Because she didn't know what day, what time, and all that other stuff. So Friday forgot to tell her. So now, to go along with that, it comes out to be how much? So each person gets 1/100th of a cupcake. Is that a lot? No, not really. That's you got a pinch. Each person could just take a pinch of that cupcake. Okay? Then we got certain people like Peter that is going to take that just all icing. That's all he did. He didn't get no cake. He just got all icing on it. He's one of those people. And so, as you know, the more and more people that we keep dividing this among, what do we know about the slices or the piece of cupcake we get? It keeps getting smaller and smaller, right? So it keeps getting smaller and smaller. So as the denominator in this story keeps getting bigger and bigger because we're dividing it among, more and more people, what is this actually going to? It's going to 0. It's approaching 0, right? Will it ever get to 0? No. And so we're talking about a limit as it is approaching 0 now. So as this goes to infinity, the limit of this going to infinity would be approaching 0. So limit as x approaches infinity of my function will give me 0. Because the denominator keeps getting bigger and bigger, so that means I keep getting smaller and smaller pieces, right? I'm dividing it smaller and smaller. So you guys conceptualize that, because every time I do that, it keeps getting smaller and smaller, and if I had a graph of it, it's going to have an asymptote right at 0. So now, on this one right here, if I square any number, it's going to be, say positive. Positive. Yeah, there we go. Square any number, it's going to be positive, right? Especially negative numbers. So when I do that, think about the numbers that are going into this. So 4 over, let's start off with negative 2. It would be over 4, which gives me 1, right? But now I'm getting to the left. So I'm going to negative infinity here, right? So all the numbers that are going negative infinity on a number line, I'm always going to square it, so that number is going to become a positive now, isn't it? That's always going to become a positive. So now 4 over infinity is going to give me 0. Yeah. We're lucky on some of these that are coming up to asymptotes, and so there's domains that we could actually use. Sometimes they don't do that. So this is one that it goes to a number. It's not going like off into oblivion, like some ridiculous. All right, how about this? Positive infinity inside this. So that means there's numbers, right? Numbers, as numbers keep going. So that means the denominator of this is always going to be positive, right? But it's going to keep getting bigger and bigger and bigger, right? Say yes. Yes. Okay, it's going to keep getting bigger and bigger and bigger, even though it still is the square root of it. It's still going to keep getting bigger and bigger and bigger denominator as I go. So now, as I do that, that's still going to be over infinity, right? So it's going to be basically saying I'm taking negative 10 over infinity. Yes? So, conceptually, what does that go to? That goes to 0. You're a negative 0. All right. How about this next one? This is actually a good problem right here. So, 3 over infinity goes to what? 0. And so it's going to be the limit as x approaches infinity of the function 2, right? So it's 2 plus 0, which gives me 2. Make sense? Good. All right, how about this one right here? Infinity and beyond. All right, so I like to cheat on this. I always do. Especially in the idea of infinity. So we're having a foot race to infinity. Okay? A foot race to infinity. So I'm always going to just look at this piece right here. The leading coefficients. The top is going 3 times infinity squared. The bottom is just going infinity squared. When we're approaching infinity, all this other stuff just goes away because it really doesn't. In the large concept, in the bigger concept, even though this says plus 2 times infinity, right? It's still insignificant compared to infinity squared. So all you have to do is look at the leading coefficients if I have a common degree. Do they both have the same degree? Yes, they both have x squared. So let's take a look. It's going to be 3 times infinity squared over 1 times infinity squared. So my limit on this one is going to be so if you ever want to play with these problems in your calculator, these are good ones to actually play with. Because if I'm taking it to infinity, just put in big numbers for your x, right? Just put in huge numbers for your x and just keep doing that. And as you go with the larger and larger and larger numbers, it's eventually just going to boil down to be 3. So, but that's a good one to play on your calculator. All right, how about this other one? Which one is it going to go to faster? Bottom, right? Leading coefficient. So foot race to infinity. The bottom is going to win. Okay? By a whole factor of infinity, right? So if it's going to negative infinity, pay close attention. So this is going to be, if I were to just like say I could factor out that whole thing. Right here, I have negative infinity to the 3rd power. What is that going to be? Yeah, it goes to negative infinity, right? Because on top, the negatives become positive anyway, right? So it really doesn't matter because the bottom's leading the foot race. So no matter what the top does, the bottom is going to go faster to it. So it's like taking 2 big dogs for a walk. Actually, no. 1 big dog and 1 little dog. Okay? So you have 2 different leashes. Which one's going to pull you? The big dog's going to pull you. The little dog's just going to follow, right? The denominator, x cubed, is the big dog here. So this one is going to go to negative infinity. Questions? No? Okay. Now, leading coefficients is what I said we're going to do, right? Leading coefficients. So let's look at leading coefficients here. So what do I really want to say the leading coefficient of the top is? 2x. Very good. So leading coefficient is actually 2x over x, right? Why am I saying just 2x? Yeah, because it's the square root, right? It's a square root. And I said this over here in the big picture does not matter. When we're talking about infinity, we're talking about like ridiculous numbers. That it's like infinity plus 1. Is it really? No, it's still just infinity, right? So right here, and so this limit as it goes to positive infinity, we get 2.
Those make horizontal asymptotes? Is that what's happening?
Yeah. So as the limit goes to infinity, this function is going to go to 2. Yes. So it's yeah. Yeah. I'm not really going to say asymptote because it will wiggle sometimes. By wiggle, I mean that in my graph, it'll go like this. So sometimes it'll go here, down, up, down, like that. It'll get closer to that. So it'll have some wiggle in it. It can go above and below, but it'll eventually, as you get far enough, okay, it will just be straight line at 2. Okay, because some of the functions, I'm not saying this one particular, yeah, some of the functions you will see that it's not really an asymptote, it's just, it's wiggling and that's what it's approaching. So, yes?
Like the alternative
Yeah.
to like the negative numbers.
Yeah, something like that. All right, so finding limits at infinity. Let's take a look. Do the test. On A, what is it? 3. On B. On C. Positive infinity. Very good, because the top is going to lead that one, right? Other infinite limits at infinity. Go. So, if I take the limit as, this is super important too, because this is actually like one of those identity things you're gonna have to understand later on. Okay, you'll be like, oh yeah, I'm looking at it, I see it, I know it's that. So this is the graph of e to the x. So as it goes to negative infinity, it's this way. Okay, which goes to 0. And positive infinity, it is going to go to positive infinity. Why oh why are they going different directions? When I have a negative exponent, what happens? Fraction, and it goes to the denominator, doesn't it? So let's say I have a negative 10. So that would be e to the negative 10, which is the same as saying 1 over e to the 10, right? Ah, crap. I know, wrong 10. There you go. So when I get negatives over here, that changes my fraction, doesn't it? So it changes this, so that means the denominator is going to keep getting bigger when I have those big negatives. So it's going to keep approaching 0. ln does not exist in the negatives. So we only could have it from the positive side here. So as it approaches, let's say we did this the other day, as it approaches 0 from the right hand side, I would say that goes to negative infinity. And then this, it just creeps up slowly, but as it goes to infinity, it also goes up to infinity. Even though it looks like it's leveling out, but it still keeps going up minuscule amounts every time. And investigate infinite limits. Right here, dissolve water into salt dissolves into water. Sodium Na positive ions and chlorine ions according to the law of uninhibited decay. Now, super important. Uninhibited. What does uninhibited mean? Not limited, right? Okay, this is going to be super important for you. So where A is equal to A of T, the amount of kilograms of dissolved salt present at the time, T hours, A sub naught is the original amount of undissolved salt. A sub naught, original amount. Okay, I don't know if you guys have chemistry. Do they write it the same way? Some of you guys probably had chemistry at one point.
Yeah.
No?
For what?
A sub naught is the original amount. The mathematical term is...
No, they were really light on math, chemistry.
Oh, I'm sorry. So anyway, again, it's called A sub naught, which is your initial amount. All right, and it says K is a negative number that represents the rate of there we go, that word. Negative. Okay, why are they pointing out specifically that K is negative here? Because this is a decay, right?
Oh, yeah.
If it was a growth, it would be positive. Okay, that's K is referring to the growth factor or the decay factor. All right, where T is going to be my time, right? Say Jess. Okay, very good. So if initially there's 25 kilograms of undissolved salt after 10 hours, there is 15 kilograms undissolved salt. Ooh, so information right here. And, ah, crap. Insert, page, after. Okay, so we have that A of 0 is, say 25. Okay, and so A of 0, so what does that actually say?
Let the original ratio.
Okay, so this is my, so A sub naught, right, is 25, and T is,
Time, which is like
say 0. It's the initial amount, okay, because you guys have to have these numbers for this. So this is actually some serious algebra here. So we have these values, so we have T is 0, A sub naught is 25, but now I also have another value. What else did I have? So I had A of, say 10, is equal to 15. All right, so that means that after a certain point, my T is 10, and my output is 15, right? Do we know the rate? Say no. Okay, right here. How much undissolved salt is left after 1 day? So I got to figure out the rate now. So given the formula, I had A is equal to A sub naught e to the k t. All right, let's start with my initial. I know my initial is going to be 25, right? Okay, so I have 25 e to the, I don't know k. Do I know t? T. T is going to be 10. But now, I know at 10, my end result is how much? 15. That's super important to understand how it's set up here. That my end result, my output when I input 10 is 15. Okay, my output came out to be 15. Yes? Okay, please speak now or forever hold your peace if you have. This is a setup. You're going to have a whole bunch of these. This is always an AP test question. Speak now. No questions? Okay. All right. What value are we trying to find? Okay. So I have to do a little math. So divide by 25. So I'm going to get 3 over 5 is equal to, 3 over 5 is equal to e to the k times 10, right? How do I undo an e? ln, right? So I need to ln both sides. I need to ln both sides, so I'm going to do that. So I'm going to say that if I ln both sides, I'm going to get ln of 3 over 5 is equal to, when I ln e, that goes away, right? Say yes. Yes. Okay, so I'm going to end up with 10k. All right, so I'm trying to find a value for k, so what would I do? Divide by? So k is equal to ln of 3 over 5 divided by 10. I'm just going to leave it in that form right now because when I plug it in later, it's going to be so much easier. And I don't want that decimal yet because the decimal means that it's been rounded at some point. Don't round until the last step whenever you can. All right, so now, we now have a k value. Say yes. We have a k value. So we have everything we need for this function. Now let's go back to the question. And it says, how much is salt remaining after 1 day? So that's your next point of information. What information did they ask for? 24 hours, right? So 24 hours. So now that's changing my value. What value do I have now? Someone say T. So T is 24, right? T is 24. So I have everything I need now. So I know I'm looking for A. So it's going to be A equals e to the, oh wait, crap. So it's 25 e to the power of 24 times ln 3 over 5 divided by 10. So that's how much salt it's going to ask for. So now this is the point that you would plug it into the calculator. Go ahead. Don't everyone jump at once. Your calculators are your friends, not food. Yes? Yeah, go ahead. Okay, so it was 25 times e to the 24 times control divide ln of 3 over 5 over 10. So, in calculus, especially AP calculus, you always have to round it off 3 decimal places unless stated. That is an AP standard, 3 decimal points. So if I were to say that, that would be 7.337. All right, anyone having trouble with the calculator? Is it milligrams?
Kilograms.
Kilograms, kg? Yeah, kg. All right. That was part A. So this is the type of question, like I said, you're going to end up with the test. But not like this, because the first one's not calculator. Next one. How long will it take until 12 kilograms of undissolved salt remains? Okay, so now, what is it asking for this time? How long will it take until 12 kilograms of salt remains? So I know that A, so I'm looking for time right now, right? So my variable I'm now looking for is time, but now I know that 12 is going to be my output, right? So insert page after. So I know that it should be 12 is equal to 25 e to the k t. So it's t times ln of 3 over 5 over 10. Algebra-wise, go through and try to algebra this to isolate your t. So divide both sides by 25. 12 over 25 is equal to e to the t and ln of 3 over 5, 10, ln both sides, so ln of 12 over 25 equals t divided by ln of 3 over 5 divided by 10. Divide both sides by all of this mess right here. There we go. So, taking care of that. So now just plug this in the calculator to get your approximation for t. And what do we come up with? Yep. 14.368. So T, and that would be, is it years or hours? Sorry. I don't know why I was thinking years. Forgot what I was doing. Find the limit as T approaches infinity. As T approaches infinity. Now, think of it like this. T is positive, right? Say yeah.
Yeah.
Okay, T is going to be positive. What about K? Is this dissolving? It is dissolving, isn't it? So that means that if it's dissolving, that is going to be negative, isn't it? So yeah, I could actually do the math to figure it out because I left it in ln form for this reason so we could see this. So it was, let's see, control divide, so ln 3 over 5 over, it's negative, isn't it? Okay, so now let's go back to the time thing again. So the time is positive, but the K is negative. A positive and a negative makes what? A negative. So I'm going to have a negative exponent on my E, right?
Yes.
So as I take E to a negative exponent, what was that?
0.
It goes 0. Because even though I'm plugging in infinity, it's infinity times a negative number. So it's going to be a negative infinity. So as a negative infinity goes to the power, right? So that means, that's the reason why I pointed it out. So E to a negative power, so a negative infinity is going to go to 0. E to the positive power is going to go up to positive infinity. So the limit as T goes infinity is going to go to 0. Interpret the answer found in C. That's my whole reasoning that I was actually explaining it like that. Because you're going to take a power, a positive power, which is those positive T's, and then you have a negative decay. So your decay will always go to 0. In these cases, your decay will always go to 0. And I think that is it. Yeah. Horizontal asymptote. Ah, crap. All right. Horizontal asymptotes at 304. Okay, there we go. All right. Bye, you guys.